Climate action plan. Back in 2008, staff, faculty, and students got together to work on our climate action plan. 2009, we finished up the plan. The idea, eliminate greenhouse gas emissions, broaden academic research, become climate neutral by 2050. So really great plan. So this was a four-tiered strategy. The first tier was to avoid new space, really utilize the existing space that we have on campus, optimize the space that we have to avoid building new space, thereby adding more carbon. Next, and that's kind of where I come in, reducing energy demand. So reduce that demand side energy, energy conservation initiatives, outreach campaigns, that type of thing. Utilize renewable electricity and renewable heat, right? So as we're kind of going down these tiers, the costs start to rise. Our payback starts to expand out a little bit. And finally, we want to offset our business travel and commuting, purchasing offsets. So that's kind of the last bit. So we want to optimize our use, reduce our carbon, and then finally, at that last little bit, that's where we'd run into purchasing. All right, so this is the plan trajectory. So if you look at the blue line, you see a nice big steep drop. That's where we basically got out of the coal business. We decommissioned our coal boilers, installed two new combined turbines, combined heat and power plant, two new turbines that produce the heat for the campus and also electricity for the campus. The next bullet, again, that's where I come in with the energy conservation initiatives. So we institute initiative plans. We bring in some solar, wind, engineered geothermal, so deep hot rock. So that's the next plan. We're in the investigative stage of that right now. And then finally, we look at purchasing offsets. That gets us right down to our carbon neutral at 2050. Currently, we're working on trying to push that up to 2035 and developing a new climate action plan. So that's in the works right now. All right. So energy conservation. Two main initiatives that we've had since 2000. The first one was kind of our kickoff. We started 2008, about $10 million worth of spend. The goal was a $1 million payback, about a 10-year return on investment. Phase two, we kicked off about 2010. A little bit of a bigger program, $33 million. The administration said, hey, if you can come up with projects that have a 7-year build payback, kind of an all-in utility cost payback, we'll fund it. So in that 5-year plan, I busily set out to find as many energy conservation projects as I could to help reduce our energy use. We looked at updating building controls, really trying to optimize how we brought air into a facility, minimize reheat, minimize the amount of time that spaces were occupied when they shouldn't have been occupied, minimize ventilation air coming in when we really didn't need extra ventilation air. We did a lot of recommissioning of systems. We found that our systems degraded over time. Recommissioning, we could bring those systems back to new, reduce the overall energy use. Lighting, we're doing a lighting retrofit LED, and I see that you guys are doing a lot here at Harvard, which is great. And we're looking at humidification systems. Humidified air, so whenever you bring in air from the outside, you heat it, cool it, humidify it, dehumidify it, you're just adding dollars. So if you can minimize that, if you can really make sure that you're not over-humidifying or over-dehumidifying, you can help drop your energy costs. Right? So just kind of the basic overall of our energy conservation program. So we had already been doing our recommissioning and continuous commissioning. So I have a staff of 10 control technicians, and their job is basically to go around campus and hit the high energy users. So we've established energy baselines for all of our buildings, and whenever those buildings start to go outside of where we think they should be operating, we will recommission the facility. So 10 individuals that about half of them look at the central, kind of the air handlers, the heat exchangers, kind of that central mechanicals, and the other half look at spaces, the VAV boxes, temperature controls. They really try to optimize, make people more comfortable while utilizing less energy. So for the conservation initiative, we completed energy studies. So as I said, we have energy baselines for all of our buildings. So we evaluated and graded all of our buildings for the energy use intensity. We took our bad performers that we thought, and we completed energy audits on them. So about 60 facilities, we ended up doing energy audits. From those energy audits, we were able to develop improvement measures. And then we can evaluate those improvement measures, whether they met our payback criteria. So we had that 7-year build payback criteria. Great, so we created programs with all of those facility improvement measures. We sent those out to design, had an engineering firm design them, reevaluated to make sure that they were still within our cost criteria. And then we sent them out to the bidding community and constructed them. Once that's complete, we went through and put them back in the pool of continuous commissioning, right? So it's a continuous cycle of commissioning your buildings, making sure that they're operating properly, developing projects to further reduce energy use, and then going right back through that continuous commissioning. All right. So just finished up the project about last year, and as we were finishing up the projects, 6 to 8 months after the project was complete, we evaluated the energy savings. So we did a weather regression on how the building was operating compared to how they operated pre-project, and found some really great savings. So we had an original $4 to $5 million target goal. We ended up with $6.3 million of energy reduction, a 5.3-year payback, and the $33 million that the university allowed me to spend. We were able to reduce steam use in the buildings that we had done projects in by 21%, chilled water by 25%, electricity by 17%. One of the things that's not really shown here, and it's really kind of hard to capture, is the maintenance that was reduced. So we ended up reducing energy, but we also significantly reduced the amount of maintenance in these facilities because we were already taking care of problems that were existing. So we ended up with safer labs, more comfortable occupants, and reduced energy. So really kind of that nice triple bottom line. This is one of my favorite graphs. It's basically right from the ECI, Energy Conservation Phase 1, all the way up through present day. And so what it shows on the left side is the total campus energy use. On the right side is total campus gross square footage. And the black line shows the campus growth. So you can see that we kind of back in 2000, we started out at a little bit below 12 million gross square feet, and now we're a little bit above 14 million gross square feet. The key part is the red, green, and blue lines, which is our steam, chilled water, and electric sales, to see that they're pretty much the same or dropping a little bit. So energy conservation basically has absorbed that additional gross square footage, about 25+% additional gross square footage. The conservation programs absorbed all of that extra gross square foot. All right. Now, to talk about what we're here, talk about labs, right? So, as Meredith had stated before, just on this campus, Cornell's campus, labs use a lot of energy. About 25% of our campus, they use about half. So it seems like we're right on about the same sheet of music. About $30 million a year of energy use in labs. So main focus for me is, hey, how do I reduce that energy use? How do I drop that bill? We talked a little bit about recommissioning lab spaces. Well, what we started looking at was, are we over-ventilating the spaces? So worked hand in hand with Ellen and her group to see if we could reduce that ventilation rate from typically 8 and 4 air changes, so 8 air changes, that's how many times a lab air is getting exchanged within a lab, occupied, 8 air changes, occupied, 4 air changes, unoccupied, down to 6 and 3 air changes, so 6 air changes occupied, 3 air changes unoccupied. So possibly millions of dollars worth of saving, so we decided, let's take a look at it. What we did was we started out with a lab in our biotechnology building. We completed a CFD, computational fluid dynamic analysis, to really see how the lab was acting. And then we did some pilot testing, and we also looked at reducing temperatures. But the key was to evaluate what the lab was doing, and then how could we improve it. So with the CFD, we kind of got an idea, well, this lab, even though the lab was actually above 8 air changes, it was right around 10 air changes. And what we found was that it really wasn't acting that well. The CFD analysis showed that a smoke test, the smoke would stay right close to the ground, it wouldn't get flushed in a timely manner, and what we found was that the supply duct layout, and this is kind of the existing, you have 8-inch round perforated supply, so the idea was to have a nice laminar flow from the supply duct out to the exhaust duct and out to the fume hood. It didn't really work that way. What we found was that 8-inch round perforated supply duct right up at the ceiling was spitting out air, and the air was going right to the exhaust, and it wasn't hitting any of the lab space. So we said, well, I think we can do better. So we did some CFD analysis, and what we found was, yep, it doesn't really work. So we did a smoke test, and lo and behold, the smoke test looked exactly like our CFD analysis, which was really cool. It was really kind of neat to watch that analysis. So this is kind of a time lapse. So at 7 minutes, so really it's kind of still staying by the ground, 12 minutes, and then finally at 20 minutes, it's finally cleared out. So it took about 20 minutes for that lab to clear out, and there's no visible smoke of that, and this is kind of a little bit of a blurry picture. Now this was at the 6 air change rate. So we wanted to evaluate 6 air change rate old and 6 air change rate new. So we did some more analysis. We looked at using a radial diffuser to kind of throw the air where we wanted it. We relocated the exhaust ductwork and then did some more analysis, and what we found was that we could improve the way that the air was flowing through the space. All right. So, and what we found is you didn't end up with that large plume right off the kickoff because the air was flushing at floor level and throughout the working space. Apologize for the dark pictures, but at 12 minutes we had no visible smoke, which validated with our CFD. So we did our pilot. One of the other things we found, so we had some control issues with the lab. We were getting smoke that was flowing into adjacent workspaces, so there was a separate work computer space off the lab that was supposed to be totally isolated from the lab. It was supposed to be positively pressurized. It wasn't working that way. Smoke was actually flowing right into the lab before. Afterwards, that lab space was clear. Right. And then this is just kind of shows the an acetone level at a half a foot off the floor, which goes along with our visual of the smoke. You see a large concentration, a little over 3,000 parts per million. Existing design versus the redesign, which we didn't really see a lot of smoke. All right. So from that, we determined, all right, this is how much it costs. So if I know how much it costs, I can start evaluating what my payback is. How do I expand this out to the rest of the building? There was 90 labs in the building, found out it cost about $2,000. It was really important to look at how the radial diffusers were sized. That was one thing that we learned really early on. We wanted to make sure that we were not disturbing benchtop work, so you had to really be careful in how the throw and velocity, also the noise. We didn't want it to be too noisy. So 90 zones, project cost about $180,000. I actually came in a little bit under that. It was about $170 by the time I got done. The workers got faster as they went through the labs. So after the initial install, by the time they hit room 90, they were just plowing right through the room, so it was really great. And it had about a 2-year payback. So really, we ended up with a safer lab, an energy reduction, so it was really a plus. And it took about three months to go through. So what did we learn? So we learned that, hey, it's possible to reduce air change rates from 8 and 4 air changes down to 6 and 3 air changes. That's possible. Just not as simple as, just go out and do it. You had to do some analysis. You had to make sure that you were taking a look at how the air was actually going to flow through the labs. So this was pretty important. Ventilation effectiveness. So 8 and 3, 6, or 8 and 4, 6 and 3. Really, that's just a number. Really, what's important is how that air is flowing through. Is the air staying up at the top of the ceiling? Well, it doesn't really matter if you have 12, 20, 30 air changes. If the air isn't getting down to the occupant space, it doesn't do any good for you. Okay? CFD analysis really should be a part of every design. Try to put that into our design standards. There is a cost, $10,000 to $15,000 per lab. However, if you have cookie cutter labs, it's really easy and it can really be incorporated into your cost. One of the things we found was that sometimes you have to change out the VAV boxes, those variable air volume boxes, the airflow control boxes, because in original designs they were oversized. So to get down from the max cooling level down to the min level, you're down below that 30% min level, and it makes it hard to control. So sometimes you have to resize the VAV boxes, so you have to pay close attention to that. Pilot installs, whenever I'm trying to do a building wide, I always try to use a pilot install. And it's very important to work with EH&S. So throughout this whole process, we worked with Ellen and EH&S to really make sure that the labs were safe, the ventilation rates met the criteria that they set forth. So, and Ellen will talk about our LVMP.
So we did a lot of work in biotech, but there was some 10 years worth of looking into this. And we wanted to replicate this across campus without having to spend lots and lots of money, but we needed to hire somebody to do that, which was my predecessor. And we needed a plan of how we were going to do that. So oh, sorry. I don't like being behind this thing, sorry. So we needed a plan on how we were going to replicate this across campus. And my predecessor was hired in 2010, and I needed a graduate student project, and I was a management student, a systems management student, and so we started working on this. It took us a good year to get it written up. So our LVMP, our Lab Ventilation Management Plan, we took the Z9.5 ANSI standard for lab ventilation and tucked it inside the Z10 for occupational and environmental management systems. We recognize that there are multiple priorities in these labs, and now we're adding sustainability to them. There are various ages and designs of our buildings. We also have an old campus, and no building is the same. They're all different. The ventilation systems are all different. The science is different that's happening in them. And we wanted to base this on continuous improvement. There are new technologies that are coming out. Many of us have been to the Labs 21 conferences, the I2SL conferences. There's different ways of thinking over the years and decades as science is changing, and we want to keep up with that. And we also recognize that there are different layers of the ventilation systems. We have a large campus, and I work at some level of the ventilation system. Mark works on a different, we have teams of people that have different responsibilities for these systems. At the macro level, you have where the air comes into the building and all those exhaust stacks. And then inside the building, you have mixed-use spaces. And there's pressurization differences between those. And then inside the lab is where the people are working. That's where I come in. Where are they using their chemicals? How is the air flowing through? How is it sweeping through the space? And then the ventilated storage spaces, the fume hoods, the canopy hoods, glove boxes, that sort of thing, and the chemical storage cabinets. Okay. So a big component of the program is this control banding. The 8 and 4 air exchanges down to the 6 and 3. What this is sort of a generic protection strategy, that just went black, where you group similar hazards into bands. And between the collaboration between my office and the utilities department, we settled on 8 and 4 as a design-to standard. And we wanted to find places where we could go down. And using CFD analysis in new projects that are large enough to that have a budget to be able to do that, that was incorporated into many of them. But moving forward, we needed to have a method of how we were going to make that decision of where to go down. But we recognize that there are plenty of spaces that are called a lab, but they're not driven by the chemistry. Our banding process is driven by the chemistry, whether it's high Has or low Has, but there are others that fall outside of that. Some of them are higher than 8 and 4. They may be exhaust driven. There's lots of fume hoods. The lab is very small, so it's fume hood driven. There's high heat or humidity loads. There's a high occupancy of humans or animals. There's different rules around how much ventilation you have to have in animal occupancy spaces or animal housing spaces. And then there's spaces like clean rooms that have specific environmental conditions. And then places where we just can't manage. We don't want to mess with the amount of ventilation because there's too much turnover. And then the labs that fall below the 6 and 3 air exchanges. They're very low hazard. There's very small quantities of chemicals. So chemistry is really not driving the ventilation rates. There's local exhaust points that actually capture the point sources. So 3D printing is the latest and greatest. It's exploding on our campus almost as bad as the nanoscience. And they're not just finding new materials to melt. They're cutting and building these boxes in their labs. So we're trying to keep up with that. And some of these spaces, like we have an incubator right on campus, we just can't manage the ventilation in spaces like that. So what we're doing is putting in local exhaust points for things like that. The human occupancy or the odor control is the main driver. Some places, they're labs, but it's an electronics lab. There's no chemistry actually happening in it. And then places where there is a high heat load, like freezer farm, there's no chemistry happening in it, it's all the heat. So if we could put in a fan coil unit that takes care of that heat, then we don't need as much ventilation. So the assessment process that I do to determine where which labs are going to be 8 and 4 and which ones can actually go down to 6 and 3, it's a 3-step process. In the first step, we're looking at the chemistry. In the next phase, we're looking at the ventilation effectiveness, which Mark touched on. I'll speak to that a little bit more. And the last step is assessing the housekeeping practices. I'm in the lab safety group. I do lots of inspections, so I'm looking at housekeeping from two different angles now. So the types of chemicals that we would have to stay at the higher levels, I'm assuming many of you have not had GHS training, but those of you that are in the labs should have. We're looking for the chemicals that have an inhalation hazard. They are extremely flammable. They're volatile. They are fatal if they enter the airways. They're fatal if inhaled. They're toxic or harmful. The ones that we're looking at that can actually go down to the 6 and 3, they're more of an irritant. But then there's other things that you have to take into consideration. The concentration of these. Does the lower concentration, when they make lots of solutions and dilutions and mixtures with the chemicals, when they do that, is it low enough that it falls outside of those hazards? The toxicity, the sensitization, or the odor concerns become less severe, or they just get diluted out. The location of the use. Are they using those hazardous chemicals in the fume hood, or are they using them on the bench top? Let's say there's a piece of expensive equipment that they have to use out in the bench. They can't use it in a ventilated enclosure. And then the quantities, very small quantities, 100 mils, the little squeeze bottles of the acetone. Or is it several liters? Is it larger quantities? And then the availability and proper use of local exhaust. That's really key for some of them with the proper use of local exhaust. If they have that elephant trunk or that canopy way up here and the process is down here, it's not doing for them what it should be. So that's part in training. And then with the effectiveness is the next step. So Mark talked quite a bit about one project where we did CFD modeling, we did smoke tests. We can't do that in all spaces. CFD costs quite a bit of money. To do hundreds of labs each year, we can't afford to do that. So we needed to come up with another way, another field test to look at how well the sweeping of the lab is happening. So we came up with a CO2 fire extinguisher test, which is a lot of fun. We have a group on campus that it makes it cheaper for us because we have thousands of fire extinguishers, and this testing and inspection group actually takes them and refills them. So we just go borrow a few that we need and bring them back empty. So what we do is, I don't know how well you can see this picture, but this was in a BSL-3 space, and we set CO2 meters around the lab at points of interest, release the carbon dioxide, and then watch the ventilation do its work. So something to keep important is that as the ventilation removes the contaminants, this is actually fluid dynamics. So we have points where the air comes in, and then we have the exhaust points, and we're looking for how well that's being pushed and pulled through the space. When you have things like equipment and chairs and for other furniture, the benches, and all the stuff, there tends to be pockets. If the lab wasn't designed with effectiveness in mind, you could actually have the benches located or positioned in the wrong way so that it blocks the ventilation from sweeping, okay? So it actually ends up being an exponential decay. When we release the CO2 in the space, we bring the CO2 levels up to about 10,000 ppm. We don't want to go any higher than that because it gets dangerous. And then we watch the ventilation. We calculate this in an Excel spreadsheet after. We watch the ventilation remove the CO2 levels down. And it looks something like this. We have to keep in mind that the ventilation controls the chemical contaminants by removing this exponential decay. And this rate of a specific chemical release depends on the location. So I said we put the CO2 meters around. What we want to find are where are those dead zones. And they're different. So if you have really good sweeping of the lab, it's going to, from a source, let's say we release here, it's going to spread out pretty evenly. But that's not what happens in an existing lab. And then we have to keep in mind that one measurement where, for example, when you measure where the ventilation comes into the space, that's not the story for the entire lab. Okay, some considerations while we're doing this test: static electricity. When you're releasing, actually emptying the fire extinguisher, there's a lot of static coming out of the horn, and that can hurt your fingers or your feet. CO2 exposure, I said that you've got to keep the levels down. We want to bring it up to a certain point where we can get enough measurement points, but we don't want to have 50,000 ppm of CO2 because that becomes dangerous. Ergonomics, some of the equipment is heavy. You need a cart. There's a lot of noise. You need eye protection. You need hearing protection. And there's dry ice flakes that spit out of the extinguishers, so we actually cover up some of the electronics. That's important when you have expensive pieces of equipment in the labs. And I don't know if I can play this. Can I play this video? Okay, that's sideways. This is us releasing into a lab. You can see that big fog. It was really loud. So in a big room like this, you can't hear just how loud it is, but it's very loud when you're in the mix of it. And we're literally down on our knees just going like this. You want to fill up the room. So this is based off an ASTM standard for, you want to have it pretty evenly mixed so that your decay curve is fairly flat. And this is what it looks like once we put it into Excel. In this, we had 3 meters. We overlay those, the curves, and then we want to see if there's any bump, why that happened, and just how long it took to remove the CO2 from the space. The goal is to get a uniform concentration, and this is indicated by just how nice and even that is. We look at the peak CO2 levels. That suggests how strong the source was. Did we actually reach 10,000 ppm? The decay rate is actually the air exchange rate at that location where that meter was. And then we want the R squared, the R squared value to be above 0.9, because that'll tell us just how good our test was. Anything below that, and we want to redo the test. And then also the amount of time to get up to so the front side of the curve is also important. So the last piece of the assessment, so there's 3 pieces of this assessment that I replicate when I'm doing inspections or out doing recommissioning with one of the controls techs. You look at the concentrations and the types of chemicals that people are using. We do this ventilation work. And then the housekeeping. So being a former lab manager, housekeeping isn't just the drips and plops and the fugitive emissions on the benches and the spots around the way stations where people aren't cleaning up. This also indicates how well people are trained. Do they understand the hazards of the chemicals that they're working with? Do they know when they have to work in a fume hood instead of on the bench? So it points to me the students that are coming through. Who's monitoring them? Who's following up on them to tell them to clean up? And that's something I can revisit with people. It's great to capture that when you're doing inspections because you get to follow up on that. So I do this during inspections, but then also the recommissioning, and this is just a chart. There's a lot of things that have to be done, and these control techs, I follow 2 of them. They can be in a building for months because it doesn't take 6 months to a year before there's lots of broken parts in the ventilation systems, and they go piece by piece looking at them. So the banding of the labs that I do is only one aspect of what they're looking at. But when they're done, the building is running much, much better, and they end up saving a lot of money because of the banding process too. Some recent ones that we've done, just a few buildings. The top one is, there's only like 11 labs in it. The other ones are older buildings, but we managed to find quite a bit of savings. And then we have this dashboard that our sustainability office worked quite hard to get up. So they do a lot of energy smackdowns and other competitions, and the folks in the labs can look to see how well their building is doing in the competition. Are they reducing the amount of energy that they're using? And this is an image of when one of those was going on, and Human Ecology building is one of our brand new buildings, and they were doing the worst. So their building controls can actually do more than the other older buildings, and I was wondering, are they not participating? It seemed like they were, but I was wondering what was going on, so we decided to go into that building and do recommissioning, and we found quite a bit. So we ended up recalibrating the SAS position sensors. They weren't commissioned correctly initially. They weren't set up right. The airflows are now ramping up faster, providing better user protection. So when somebody opened the sash, it was taking a long time for the airflow to increase. That's a safety value. And through the control banding, we ended up saving almost 16,000 cubic feet per minute. We also corrected the minimum exhaust flows for the fume hoods. That found some savings. And then just other issues. There were some space temperature controls that when they were fixed, and these were in the hallways, it provided more stability. And here's an image of the before of that instability, and this is what it looked like after. It was actually moving up and down in a much smoother fashion, which is what we want to see. So some of the triggers, like that energy smackdown, I noticed something wasn't quite right. Energy projects. When Mark is doing his work, we might actually go in and do our work in-house. Space changes. It's really important to keep up with the management of change in the lab. So we get these big wins when we recommission a building, but later on I have to go back in and look at the space again because the science is changing, students are moving through and graduating. And then just complaints from occupants. I don't ever want to hear a complaint from somebody in a lab because we reduce the ventilation. We want to be responsive to that. And then just revisit because during inspections, and then just doing the recommissioning so we can just look at them again. So all of this work has been going on for like 15, 16 years now. A couple years ago, we wanted to bring in some operational sustainability actions that the folks in the labs could do. Many of our campuses are starting these Green Labs programs, and year over year, we're seeing them getting more and more sophisticated. This is something new to the folks in the labs. It's easy to have a green office program. There's some basic things folks in the offices can do, but it's a lot more murky in the lab setting. And it's also something that a lot of the lab folks don't even want to think about. They want it to be easy. If it's that important for them to look at, we got to make it easy for them to do because they're there for their research. And they certainly don't want sustainability efforts to impact their research because they will just dismiss it. But when they do, it's an above compliance thing. So people in EH&S, we're always harping on them for compliance. This is something in addition. They actually reach compliance when they're thinking of sustainability. It's a triple bottom line thinking. So a green lab, what is that? It's one that actually takes that effort and looks at its environmental impacts as well as the health and safety of the folks that are working in the lab, of its operational decisions. And once they do that, that gets handed down to the next generation of PIs that they're training. It acts as a leader. So we do have a certification piece. They're acting as a leader, helping people, the students and the labs next to them, incorporate these sustainability efforts. But when they get certified, they get a plaque with a certificate that actually shames their neighbors into doing that as well, which we like. And we also have they understand that this is coming from the top. The Climate Action Plan was signed in the mid-2000s. The energy conservation work was going on for years before, but we have the support from the very top of our university. So it's getting farther and deeper into all of the operations on our campus. So some of the goals, how can this help? We recognize the greening of the work that's going on in the labs already. We know that some of the folks are already into this. We want to bring that out, give them a shout out. We want to provide the resources to educate the community on energy conservation. So at my table earlier, there was some talk about a sash management campaign. We do those, but it goes much broader than that. You can't just keep telling people to shut the sash. There's other things that they can do. Some labs don't even need their fume hoods. And then identifying greening opportunities from our national peers. Any of you that have Green Labs programs, we've probably looked at your website and we've steal whatever we can from you. So we have different levels for the certifications. And we have a scorecard that either I could go walk through with someone in their space, because I always find more things and we can talk about what they can do, but they can also go through the scorecard themselves. We also have resource guides, and some of them are on each different focus area. And we keep updating these as new things come about. But these are the different areas that we focus on. Some of the goals are supporting the general ventilation rate reduction. To me, I do ventilation and chemical hygiene, so it all comes back to ventilation to me. Consider green chemistry principles. So I said this is above compliance. When you do green chemistry, one of the principles is to reduce your waste. When you reduce hazardous waste, you're already above compliance because you're not generating it, so those rules just fall out. This minimizes also, maintaining an inventory. Not all of our labs do that, and we have a very hard time mandating that with over 3,000 labs. But when they do, they minimize the chemicals that they have on hand. And then storing and using chemicals appropriately. When they do that, they don't have extra hazardous waste because something got damaged. Reducing the plug load and the heat. Maintain a sample inventory. The cold storage is our next big project to reduce. When they actually have an inventory of their samples, they're going through them and getting rid of the stuff that they're no longer in use. This consolidates, and the long-term cryogen storage for historic samples, we have an old campus too, and there's a lot of samples that could be used and researched decades from now. We want to know what those are, and then put them in more energy or less energy-intensive storage. Some recent things. So in our design standard, we do have a piece where we could, instead of commissioning a fume hood at 100 feet per minute face velocity, we could do that at 80 feet per minute. What I would like to see are more of those high performance hoods. So doing conferences, like at the I2SL or Labs 21, we see that the technology in those has come a long way in the last 5-10 years, and those are more likely to contain the chemical vapors at 80 feet per minute than the standard hoods. So we may not consider going down to 60 like some others are, but I would like to see more of those because we're more likely to have better safety around those. Updating the resource guides is something that we're constantly doing. Developing an ultra-low temperature freezer guidance and awareness. I have a group of undergrad students that are doing that right now, a team of them. And then developing campus-wide hazardous gas standards. So we have lots of hazardous gases. I'd like to do something other than just put them into a gas cabinet at 300 cubic feet per minute. Fume hood hibernation is something that we've developed, and I know others are getting on board with that. This is the temporary turning off of fume hoods that are not needed. And then Green Labs becoming more commonplace. I am seeing that. Even though we don't have very many that are actually certified, there's a lot of interest and questions around it every year. Okay, I don't know how I did that. So if you're interested in seeing what we're doing, okay, I just went back to the beginning. We do have that assessment process that I spoke in depth on. We do have 3 publications. They are for anybody to take. They're off of my website, the Cornell EHS website. I have a lab ventilation page, and they are all up there for anybody to take. And we'll take any questions, and thank you for inviting us.